Okay, so we'll go ahead and get started, everyone. My name is Vince. I just want to welcome you to this presentation of Novedge's Best of the Best webinar series. I want to thank everyone joining us today, tuning in. We're excited not only to present Scan&Solve, but to have Michael Freytag on board presenting, showing us the ropes, the ins and outs of the software. Before we get started, I just want to give a little background on Michael. He's the Director of Development at Intact Solutions and is the Chief Architect of the Scan&Solve system. He's also an experienced designer and craftsman who is passionate about bringing to life conceptual designs physically and virtually. He currently holds a PhD in mechanical engineering and a master's degree in computer science from the University of Wisconsin. Great to have him on board. Michael, if you want to give a little hello to everyone.
Hello, everyone. Thank you all for coming.
We also have Vadim Shapiro, who is also from Intact Solutions. He'll be on board helping with some of the questions and some of the discussion at the end. Michael's going to speak for about the next 40 minutes or so. During that time, everyone will be in listen-only mode, but please feel free to shoot all your questions into the question box. Afterwards, we'll open it up for a Q&A. We'll get to as many questions as time allows. We will be recording this webinar, and I'll give you guys complete details on where you can find it after Michael's done with his presentation. But having said all that, I want to turn it over to Michael so we can jump right into this.
Okay, thank you, Vince.
I'm going to switch the screen to you, and you can take it from there.
Okay. Okay, thank you, Vince. Hopefully everybody can see that I have Rhino running here.
Yep, looks great.
Okay. So let me get started. My name is Michael Freytag, as Vince mentioned, and I'm the Director of Development at Intact Solutions and the Architect of Scan&Solve. So you probably all are wondering, what is Scan&Solve? It's a software that makes structural simulation very easy. It allows us to predict the deformation of shapes under load, predict the performance, and designers can use it to prevent product failure. And it helps anyone learn insight into the physical behavior of shapes and study the effects of changes in material, geometry, loads, and restraints on the shapes that people design. It also helps build intuition into the elastics of structures, the way loaded shapes deform under gravitational or other types of loads. So let me go through a few of the benefits of Scan&Solve first. It's very powerful. It's got the power of validated FEA behind it. It's also very, very easy to use. It overcomes the complexity of traditional analysis, and as well as the difficulty of doing hand calculations in most cases. It's also very quick to learn. We try to make the interfaces minimal as possible so that there's a minimal number of controls to do what you need to do. And we found that it's an invaluable tool for education, for educators to convey the abstract mathematical concepts of structures through visual examples. And it's also valuable for students to compare and contrast the idealized models of reality that they are used to playing with beam models, for example. And they can connect that with reality, the reality of how things behave in physical reality, and they can all do all of this virtually. And professionals can also use Scan&Solve to study the behavior of the shapes that they design for end use by consumers to ensure product quality and to save time. So we've got a worldwide network of people using Scan&Solve, from architects to mechanical engineers and designers, to industrial designers, manufacturing engineers, civil engineers, engineering educators, and students of engineering, architecture, and art. I'm going to be aiming today's presentation primarily at that last group of people, because most of the people in the upper part of the list are pretty familiar with structural analysis, and I think we're trying to convey the importance and the ease of use of Scan&Solve for performing analysis and as an educational tool for everyone. So let me jump into a live demo right now. So right now what I've got is Rhino 4 running, and you've just got a, we just see a simple model here. It's just a bar, just a straight up bar. So let's get started using Scan&Solve. There's two ways to get Scan&Solve started. One way is to type S then S at the command prompt, or you can choose the S&S toolbar icon. I'll do that here. So we select that tool and choose our solid. So all we have to do here is work left to right, choose material for our component here, this particular bar is made of. I will choose an aluminum. And then we have to choose a location where it's going to be restrained. I'm going to choose this end right here. Now I have to specify a load. So in this case, I'll just choose gravity. I can choose a resolution. I'm going to run this at the minimum because it's this is a live demo. We want it to be speedy. So now it's ready to go. The go button is enabled. So I hit go, and Scan&Solve is now computing the deformation of this bar under its own weight, acting in the negative z direction. When the results are ready to view, we can switch over to the View tab, and we see our results. The most obvious result we'll see here is the displacement. So under gravitational load, it's fixed here on the left end, and the gravity, the weight, the density of the material is pulling it down. I can simulate that effect by using the deflection slider, and you should be able to see the deformation zoomed in or magnified by a factor of 34,000 in this case. So immediately what we've done is we've done an analysis. We've done, congratulations to us, we've completed our first structural simulation. So now let's explore the Scan&Solve interface just a little bit more. At any time, if you need help, you can always go to the question icon up here in the Scan&Solve dialog, and this will bring up the online help off of our website. It's organized into categories. It's very easy to follow. You can also access our documentation from, we have a documentation tool here, which is, you can click, and that will take you to the same page on our documentation. And if you're the command line type of person, you can also type S&S docs at the command line, and that will bring up the documentation. If you want to join our community, which I highly recommend, you can click on the globe icon, and that brings up our online forum. So you can join into the discussion, ask questions, get answers, answer questions. And we highly recommend that you join there. So let me go back to the beginning here. So the specified tab, there's a few controls here that I want to explain. Done, if I click on done, done will exit me out of Scan&Solve and save the results to the Rhino document. Purge erases the results from the document so that this will save space on disk as well as in memory in case you want to run larger problems. And cancel will allow you to exit out of Scan&Solve without making any changes to the problem setup or the model at all. You can also use the cancel button while the solution computation is in process to interrupt it if you noticed a problem with the problem setup. So one of the beautiful things about Scan&Solve is the ease of use. So I've got this simple geometry. It's restrained on the end. Now suppose I wanted to simulate another situation. Say I want to restrain this other end. That's easy enough to do. We just choose the add button and choose the other face. And now it's restrained at both ends. Hit go, and in a second or two we will see the results. And again, this is on the total. This is showing the total displacement. So if I slide the deformation slider, the deflection slider, you can see how this shape deforms under its own weight. It's very easy to modify the problem setup. So if I choose this particular restraint on the right end, I can edit this restraint. And in the restraint editor, I can change the name of the restraint to anything I want. And I'm going to change this one to restraint in X only. And then I can also modify which direction this end of the beam is restrained. So if I choose restraint in X only, I can disable restraint in Y and Z. Choose OK, and now you'll see that the glyphs indicating the restraint has changed to red only, so that's the cones pointing in the direction that the restraint is applied. So what this should do is allow this end to slide up and down. The other end is fixed in all directions. Again, I have gravity load, hit go, and we'll see the results in a second or two. Now if you observe, we have the same shape, or the same beam, but the deformation, or the restraints that I've applied have prevented this end from moving in the X direction. So there's no rotation at all, and it helps you see what these different restraints do, and it's very, obvious it's very quick. So this is a classic cantilever example. And we can, with version 1.4, we also have the ability to do a simple beam, or a simply supported beam, by restraining edges. To restrain edges, we choose Add to add a restraint, and you choose linear edges from the command line. And at this point, you are telling Scan&Solve which edges you would like to restrain. Choose OK, or hit Enter, and you'll see that we have the glyphs indicating that the ends of this beam are now restrained. Again, it's still a gravity load. I hit Go, and we'll see the results. What we should expect in this case is that the beam will be, the ends will now rotate because it's simply supported, so it rotates around the ends. This is a new feature in version 1.4. So that's Scan&Solve in a nutshell. Suppose we have a more complex example where we have different types of supports where we're not simply supporting the end. In that case, what we need to do is modify the geometry slightly. And to do this, what we will do is choose Solid Edit. What I'm going to do is edit a face, so that I'm going to end up putting a pinned restraint at this edge and like a roller restraint in the middle of the bar. So I'll select the bottom face. Oops, not that face. And now I split along an axis. And if I rotate this around, you'll see that I have, now I have an edge in the middle that I can apply a restraint to. Now this other restraint set already has both ends, so I need to clear this one. So I need to add some new ones. I'm going to restrain this linear edge over here. And I'm going to add the equivalent of a roller, the equivalent of a roller restraint right in the middle. So this is the restraint in the middle. I'll edit it. I'm going to restrain this to call this a roller. And what I'm going to do is restrain this so that it cannot move in the Z direction. So this is the equivalent to having the end down here pinned and a roller passing along the y-axis underneath the middle of the beam. Again, we're still using gravity loads. We look at the results, use the deflection slider, and you see how this beam would act, a magnified view of how this beam acts under its own weight. Now inside the View tab, there's some extra controls that we have. We can change the component that we're displaying, So right now we're showing the danger level. The danger level is the closeness of our material to its breaking point. In this case, everything is blue, so everything is safe. So if you look over at the legend, blue corresponds to a very low danger level, which means that we're very low, that we're not very close to exceeding the capacity of this material. If we switch to total displacement, we see again the end is displaced a lot, that you would expect. And over on the right-hand side, we have the marking buttons. What we can use these for is to mark locations on the model where we want to display or query what the component is that we're displaying, the magnitude of the component we're displaying. So min chooses the minimum, shows the minimum, which in this case is essentially 0, where it is fixed at the end. Point allows us to choose a point on the model. Turn off O snaps. So you can query any point on the model and find out what the value of the currently displayed component is. Max shows us the location of the maximum of the currently being displayed component. And the clear button will clear them all. So let me do that again. So clear clears the leaders from the document. If we exit out of Scan&Solve without hitting clear, it will, those are inserted as leaders, so they're a permanent part of the document. Another nice feature of Scan&Solve is the ability to look inside of the geometry and see how things, how the solution is distributed within the geometry. So I can turn on the section plane to do this. This section plane is dynamic. You can slide it around with the slider, and you can change the orientation to align with the coordinate axes. I will come back to this in a later example because it will allow us to look inside of other shapes where the field is actually a little more interesting. So that is a summary of the different types of restraints that we can apply. We also maybe want to be able to apply different types of loads. So I'm going to delete this roller restraint and add a restraint at the end here. I'm going to make that into a roller restraint in the Y direction or in the Z direction. And now we can add other types of loads besides gravity. I'm going to turn gravity off and choose to add loads. So when I choose to add loads, it prompts me for faces to load. I'm going to load the top face of this beam. Right-click to complete that selection, and I'll enter a load description. I'll load top face. And we've got 5 different options here for applying loads. We can apply a vector force, which is a force in a certain direction. The first option is to enter it by component. So I can enter here 20 pounds in the X direction, 10 pounds in the Y, and 50 pounds in the negative Z. Now this is not the most intuitive way to enter force components, so we also have the option to enter them by a vector force, direction, and magnitude. If we select that one, we can choose the direction by clicking the direction button. And what we're doing now is choosing the direction by picking within the Rhino document. In this case, I'll choose this corner for the tail of my direction, and I'll choose the other corner for the head. I enter a magnitude, and you'll see that the force, the glyph, the picture has updated to indicate my new direction. A scalar force is a force that gets applied directly into as if you're pushing onto the surface. So I can say if I put 200 pounds here, this is 200 pounds directly into the surface. Pressure is similar, except this is, you're doing this pounds, in this case it would be pounds per square inch, or force per area, as you would expect a pressure to be, like you see with say a tire or a basketball. We can also apply torque, but I will come back to that in a minute. So I will go back and I'll choose the original, the first one, hit OK, hit go, and we'll see how the shape deflects under this particular load. Turn my section plane off, turn my deflection on, and this one's a little bit maybe not intuitive, because all I've done is I've fixed this bottom end, and most of my force is actually in the Y direction. So let me go back and clear these restraints out and make this into a cantilever, and then the results will be more along with what you'd expect this to be. Now, one of the things that users often would like to do is apply concentrated load. The facility is not currently in Scan&Solve to apply concentrated loads, but you can get around that by doing the same thing we did before to apply the roller restraint in the middle of the beam. What I will do is insert a curve first. Say I want to apply a load at this part of the beam. So what I'll do is I will split this top face with this circle and apply a load in that location. So solid edit, faces, split face, top face, and now I choose a curve from the command line, from the options there. And now you see that I've inserted an extra face onto the top of my beam. Now whenever you do this, you have to be careful, because the face structure or the face ordering may have changed. In this case we're okay, but you do have to be careful and make note of when the face ordering changes, it's possible that the boundary conditions may jump around. So just be aware of that. So I'm going to add a load to this face, this small face that I created. This would be a concentrated scalar force, for example, of 2,000 pounds. And while we're in here, I will point out that we can also choose different units. If you choose, if you're comfortable with different units than what I grew up with, you can choose meters, centimeters, millimeters, foot, pound, seconds. These different systems of units. And if you choose a different one, it allows you to enter the force in the units of your choice. So in this case, that's 2,000 newtons. I choose OK, hit go. And in a second or two, we'll solve. And you can see the effect of this force on this structure. And if we want, we can turn on the clipping section plane. You can see how the force is distributed, where that force is actually being applied. Now, inside this View tab, we also have the Advanced button. The Advanced button switches over to a different type, allows more controls for the view. When we do this, we can change the legend scale so that the color scale that's used for the legend. So I can switch to a stepped color scheme. I can also change the dimension, the maximum and the minimum of the legend, so that you can gain some extra information about So you can zone in on or hone in on particular ranges of values. In the advanced view as well, there are a lot more options for solution components to display. In this case, we can switch over to the von Mises stress. So this is actually a computation of the stress within the shape. And again, I can adjust the magnitudes, minimum, maximum. I can choose principal stresses, principal strains, the component stresses, as well as the danger level. So everything in the simplified view is available as well in the advanced view. Now, if I've made modifications to these ranges, or I've chosen a different color range and I want to go back to the default, I can choose the reset button. The reset button will reset everything to the default ranges. So that resets it for the current component. Reset all resets it all for all components. So before I was displaying, what was I displaying? A danger level. So if I go back to von Mises and then reset all, when I go back here, you'll see that the range here has been readjusted automatically. So reset all resets the modified components for all components. Some of the other options here are we can bake. Baking allows us to insert the deformed geometry into our Rhino document. So we can do it either textured geometry or as plain geometry. So if I insert it as textured geometry, I choose a location for the texture. Hit OK. And if I switch this to rendered view and exit out of Scan&Solve, you'll see that my deformed view is still available, and you could perhaps use this for modification. Another option is to go in here and you can bake to a VRML file, which would be something that you would maybe do for distribution on the web, so that you would use like a plugin, a VRML plugin for displaying it in web browsers. It's also the file format that's often used for prototyping with color. The bottom section we have plain geometry, so you can export just a Rhino mesh object, which would be the same mesh object we had before. It just would not have color. We can also export this. That bakes into the Rhino document. The bottom three options, VRML 2, STL, and PLY, export to an external file, which you would choose in the dialog here. Another nice feature of Scan&Solve is the reporting options, or the reporting option. So say we've chosen our view. I need to clear out this one, get rid of this geometry, go back into Scan&Solve. It's very easy to generate reports. The report is simply a web browser viewable document that saves or contains the summary information about the analysis that you've just done. So I choose a name for my report, choose save, and as it saves it, after it has saved it, it opens it into the web browser. And if we look at the report, we see at the top we just have a geometry. So we have just basically a summary, some physical information about the geometry we're working with, the material properties we've chosen to perform our simulation with. In this case, it's an aluminum. It also gives information about the loads that are currently applied to our geometry. We have one load. It's a scalar force. It's 2,000 newtons. It's called load 2 in this case. Restraint. We've got one restraint. It's identified as number 7. They're just allocated in order, numbered in order. You can change the name to whatever you would wish. And it's fixed in X, Y, and Z. The simulation summary gives us some technical information about the analysis that we've just done, the degree of the basis functions we're using, and some more obscure things that you're probably not all that interested in. It also gives us information about the units. This particular one is done in inches, so our math is a slinch, which is a little odd, but that's the way it is. We also have the simulation results. We have the displacement summary, as well as an image of what the displacement looks like. And the last section is our danger level, which gives us a graphical depiction of what the danger level distribution is, as well as a summary of the magnitudes, the minimum and the maximum, as well as their location. And at the very bottom, we've got the extrema result of the results, so the displacement in each direction, and the magnitudes of these values: von Mises stress, maximum principal stress, danger level, von Mises. So one of the load options I did not discuss was the torque, which is a nice little feature. I'll just create a nice little shaft here. Choose Scan and Solve on this solid. Choose a material for my shaft, steel for this one. What I'm going to do is restrain the bottom end in all directions. And now I want to add a load. So I'm going to add a load to the top face. Select that face, and I'm going to apply a torque. Now, to apply a torque, we need to choose an axis. So what I'm going to do is choose the bottom of the cylinder and the top end of the cylinder. And using the right-hand rule, we apply a torque. We can apply a torque to this top face. So I'll do it 2,000 inch-pounds to the top face. And you can see our annotations have updated to point in the direction that our torque is being applied. And I hit go. Now, normally what we would want to do while it's running here, I will discuss this, is adjust the resolution. What we want to do is try different resolutions, try a different range of resolutions to get comfortable with the solution that Scan&Solve is computing. It's using a numerical approximation, so it's a good idea to see how the results are converging over time using different resolutions. My results are available now. I can choose to look at the deflected view. It's a little messed up here. It's not obvious. It's twisting around the axis, which, because the twist is projected linearly, it actually looks like it's expanding. And if I turn on the clipping plane, you can see what this distribution looks like inside. And I'll switch to a more interesting component like von Mises stress. And what you'll see is that this is exactly what you would expect. The stress down the middle of the object is very low, or zero, and the maximum stress is on the boundary. Now, so far all I've been doing is simple examples that can also be done analytically. But through the power of Rhino, we can actually modify our geometry and do things that we can't compute by hand. So what I'm going to do here is insert a keyway into this shaft by, oops, so I'll go back to the solid menu, solid, oops, difference. I'm going to subtract this key or this cutter shape from my keyway or from my model, which gives me a keyway in the side of the shaft. I go back into Scan and Solve. Now my modification, or I no longer can view my results because I modified the shaft. So I hit Go, and without making any changes to any of my settings, I'll see what the stress distribution is inside of this shaft because I've added that keyway. If I turn on the section view in the Z-axis and flip it so I see the top end, and switch to the von Mises because it's more interesting, you can see that the addition of the keyway has increased the maximum stress where at the bottom of the keyway. And around the edges where there's no material to carry the load, it's very low, or the von Mises is low. So at this point, I guess I would like to see if anybody has offered any questions or if I confused anybody. If Vadim or Vince could let me know, I'd appreciate that.
Yeah, so far no questions have come in. If anyone wants to shoot them in now. The only thing was from Leslie, and it was more of a suggestion. It said, tell Michael to turn off the ISO curves of the bar and properties. It will make the edge he's restraining more obvious.
Oh, okay. Thank you. Yeah, I did. I chose that example poorly. I put the split curve right in the middle of the bar, which lined up with the ISO curve. I apologize for that.
No worries.
Can you show the action on that the keyway? Sorry.
So yeah, there's a section. There's a section from the end.
In deflection view.
Oh, in the deflected.
Oh, I see. Now you see it rotating. Because it's hard to see the rotation of the cylinder, you know.
Yeah, it's hard to when the cylinder deflects, it's not obvious.
Okay, so we got some questions here. You want to jump into them?
Okay. Yeah.
Yeah, the first one's from Harlan. He says, can you use multiple materials?
Not in the current version. That's very, 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 very high on the wish list. That will almost certainly be in version 2. We're working on getting everything into this one that we can, but the architecture is going to have to change considerably for multiple materials. So that will be in version 2.
Michael, are you planning to show other examples?
Yes, I'm going to go on with more examples.
Questions about his demo right now. If there is any questions that people did not understand about the example or specific suggestions or questions about the examples, and maybe we can save the general questions towards the end.
Okay.
Let's see. Most of them are pretty general. If you want to jump into your next one.
Okay, I will continue on, and then I'll reserve those questions, the general questions, for the regular Q&A at the end.
Okay, great.
Okay. So one of the powerful things about Scan&Solve is it allows us to get an intuition about how different shapes behave to loads that might be applied by their environment. In this particular contrived example, I've got a shape which I will turn off the ISO curves so that maybe I'll turn those off so you can see my shape. I've got a couple different, I have 6 different beams sticking out of a bar. So what I'm going to use this for is to compare the performance of these different shapes under identical loading. So what I'll do is select this solid, choose Scan and Solve, and in this case the material doesn't really matter. What I will do is choose a steel, and I'm going to add a restraint on this back face. So now that face is fully restrained. Now what I want to do is add a load. What I'm going to load up is this end face on all of these models. And I'm going to load these in the negative z direction with a vector force of And while I'm here, I'll point out the per face option. What this does is on the vector forces and the scalar forces, it helps, or it determines whether the force we're applying is distributed among the faces. So if I am applying 200 pounds distributed evenly among the faces, or if it's 200 pounds applied to each face. So in this case, I want to apply 200 pounds per face. So I'm going to apply 200 pounds to the end of the cylinder, 200 pounds to the end of the square, and similar on down the line. Choose OK. So now our load has been applied, and hit go. This one will take maybe a little bit longer, but the results will allow us to actually get a good feel for how these different shapes, beam shapes, perform. Some of the non-obvious things are the fact that these asymmetric profiles actually deform, they actually twist as they get loaded. I will switch this to just total displacement, and you'll see that the angle down here at the end has a very high displacement because it's twisting so much. Next down the line, we've got the channel is not deformed quite as much. And if I want to look, if I'm interested in the actual distribution of the von Mises stress, I switch to the advanced view and go to the show the von Mises stress, and you can see that the angle at the end is under the most stress. So far all I've done is, your typical analytical examples that you can do analytically. But the powerful feature of Scan&Solve is that we can actually modify this geometry very easily and see what happens. So what happens if I drill a hole through all of these? Which one performs the best then? Oops. I'll do that by churning off O-snaps first. This is your typical Rhino modeling tools. So now I've got a cylinder that goes through all of these, and I will subtract this cylinder out to, to simulate the process of drilling a hole through all of these beams. Now I run Scan&Solve again, check my boundary conditions. The back face is still fixed. My load is still applied to these front faces, and I can hit go. And Scan&Solve is chunking away here. While it's doing this, I will show that Scan&Solve just isn't just for these toy problems. Here's an actual industrial example provided to us by Ian Boyd, who is also a member on our forum. Ian Boyd works at a chair manufacturer, and he has reduced his defects from 5% to sub 1% since he started using Scan&Solve. In this case, I believe this is a clip. The material is nylon, and he's included this arrow so you can see what the boundary conditions are. It's a load that's pressing down on this clip, and you can see the deflected shape. One of the more complex, really complex ones is also provided by him is this chair frame. In this case, this is showing the danger level for von Mises with the material of mild steel. This is a chair test where the chair is leaning back as if you're simulating someone leaning back in the chair onto the back legs. And you can see in the back of these legs, his danger level is relatively high. In fact, if we choose the max button, we can see that the maximum occurs right at the join, and it's at almost 2.5 times the strength of the material at that point. I'll go back to my other example that's now computed and look at the results. Switch to advanced view, live on my stress again, and we can see that the distribution has changed quite a bit. We still have some high points. If I made my hole a little bit bigger, you would be able to see that the stress concentration is right around the edges of this hole, as well as in the edges of this hole. When I change the magnitude, it kind of hides those a little bit. So back to the complicated examples. Here's a civil engineering example. I just cooked this up the other day. In this case, this one is made of concrete, reinforced concrete, simulated. Review the results, and it's obvious that I'm not a bridge designer because in this case, red is where my material is going to fail, which corresponds to locations where this bridge is in tension. And as I deflect it, you can actually see where those locations. You can see where things are being stretched, as opposed to being compressed. There's also an example from, I think it's in Rhino 4. Here's a nice example. I mean, this is not a problem that you can compute analytically. Deflected view. You can actually see this is a distributed load across the top. And one of the last ones is this drill body from McNeil and Associates, the Rhino people. So this is a real-life industrial example. This one again this is nylon. You can view the results. You can see how this thing will deform under a drilling load, assuming that you're holding it down here at the handle. You can see that the top bends back. Now, one thing I haven't talked about is more advanced features or more advanced loadings. If I go back to my original example, one of the things that we often want to do is to be able to apply body loads. Body loads are things like, say, an earthquake load that you might apply to a building, or say this shaft is spinning and you want to see what the centrifugal force on the shaft might be. So to choose a body load, we click Add in the Specify tab, and we choose the body option from the command line. In the body load creator, we can choose a rotational load or a linear acceleration load. Linear acceleration load would be one you might use for an earthquake. To activate it, you click the active checkbox, and then choose an axis around which we're going to rotate. This body is going to be spinning. So this is equivalent to taking the restraints and then taking the restraints to twist the shape. And I'm going to put this up really high, and I'll hit go. And what this is, this probably won't do anything, but I'll just demonstrate that it can be done. if I chose my magnitudes right. Yeah, I don't think I did. If I had gone high enough, this would actually, you would actually see this thing expand because of the centrifugal force acting on it. So that pretty much covers all the stuff that I wanted to cover. I think you'll see that this could actually be a very valuable teaching tool, both for professionals and for students and educators. Lost my notes. You'll see that the results are very easy to obtain. They're virtually painless. It's one of the, I think, one of the most powerful teaching tools out there for structural mechanics because it's so easy to use. It gives insight into a lot of advanced topics without requiring a lot of heavy mathematical background or any heavy background in structural mechanics. So in conclusion, if you want to learn more, now we'll open it up for questions and answers now. You can download the software from our website, listed there. You can join the community at scan&solve.com. That's our forum, or you can contact us directly by email.
Great.
Thank you.
Yeah, thank you, Michael. Let's just jump into a few questions here since we're running a little short on time. Here's one from Mark. It's sort of a three-part question. He says, how easy or difficult is it to add materials to the library? Are there material sharing areas on your website? And are there people using products in yacht design?
There are people using this in yacht design. You have to email me for the connect for those people because I don't know offhand who, I don't have them at hand.
If you go on the Tax Solution website, there's also a list of people who are using it. You'll see a number of marine designers. They're listed on our webpage under users or community. I can't remember.
Okay, great. Here's one from Radislaw.
Okay, there was a question on materials.
Yeah.
Hold on just a second. It looks like for some reason Rhino stopped responding there. I'll do it in here. If you start something is
System crashed.
Something's crashing.
So the answer is yes. It's very easy.
Yes.
Custom material. There's a custom button right next to the material menu. If Rhino comes back for Michael, he can.
I'm getting. Yeah, I've got something.
Why don't you just restart it? Maybe we can take other questions.
Yeah.
Okay. Yeah. I think my computer's actually dying right now, but.
Okay. Here's one. Here's one from Radislaw. It's just, will Scan&Solve be a part of the Grasshopper components in the future, or is it already? I don't know if either of you want to speak on that.
It is not currently.
Did we lose Michael?
I don't know. We might have. Michael, are you there?
No. So it's currently not integrated with Grasshopper. This is Vadim Shapira, sorry. So I'll take over and try to answer the questions. It is not currently integrated with Grasshopper, and we are working on making Scan&Solve scriptable, and perhaps we'll integrate it with Grasshopper in the future version, but not right now.
Great. Here's another one. This one's from Duke. He said, is it possible to apply orthotropic materials like wood and define the grain direction?
Version 2. Have to wait for version 2. Not in the current version. Current version can handle only isotropic materials. One of the reasons we haven't done it yet because as soon as you start doing non-isotropic materials like wood, you probably want to do an assembly, and the current version handles only individual parts. So soon, not there yet.
Yeah, look for version 2. And Vadim, I asked Vadim earlier, he said 3 to 6 months for the next version. I don't know, if, Vadim, if you want to speak more on what might be in the next one or what you guys are
Yeah,
doing now.
I guess I wouldn't want to sign for that. I mean, we're working on it, but I mean, we expect it's going to be multiple months, so it's not tomorrow. We don't. The intent is, if you look at the history of how version 1 evolved, we pretty much have been adding lots of capabilities on visualization, type of conditions, type of restraints, and so on and so forth, all in version 1, and this kind of updates are always free. We are saving version 2 for truly new functionality, which the current intent is to include non-isotropic materials and some form of assembly.
Okay, great. I don't know, Michael, are you back?
I'm back.
Okay.
Sorry about that.
No problem.
I think it's a problem with OpenOffice. It just seems to have died here.
I'm going to switch the screen back to you.
Okay.
And maybe we can get to one other question.
Okay. So you should be able to see Rhino right now again.
Let me see here. Yeah, I think, yeah, I can see it. Yeah, okay. So yeah, we're back. Okay.
Okay, so there was a question about materials, whether they're customizable, and I forgot to cover that. The materials are customizable. If you go to the material drop-down, the very first option is custom, which brings up the material editor, and you'll see all of the materials that are included. They're listed here. So you can choose to copy these over to modify them, or you can choose to copy them over to edit them and replace the existing ones. Once you've made these entries by getting the material properties off of like MatWeb or from manufacturers, you can choose to save it and then hit OK, and it'll update the database. If you also go to our forum, there's a website or there's an application there to import SolidWorks files or SolidWorks material files.
Okay, great. I think since we're running out of time, we'll just get to one more question. This one says, Scan&Solve prompts you to select only one object before applying a load. How can we simulate a more fluid shape that has been modeled using various modeling commands?
By fluid shape means collection. Right now, the Scan&Solve in this version of Rhino assumes that the object you're working with is a single solid, a valid solid. There is also a procedure to convert a valid mesh into a solid. So when somebody says a more fluid object, I assume they mean an object consisting of multiple parts, which we commonly call assembly. So that's version 2.
Okay. Yeah, they just gave a little follow-up. That's what they were talking about. So yeah, again, look for version 2. So I think we'll have to cut it short there just because of time constraints. Again, I want to apologize to anyone who didn't get to during the Q&A. Again, feel free to email either Vadim or Michael. They would love to hear from you guys if you have a question that's really pressing and you need to get answered. I'm just going to switch the screen back over to me and we can give a little send-off here. Let's see here. There we go. Okay, so again, thank you, Michael, Vadim. Tremendous presentation. Again, sorry we couldn't get to more questions. We just ran out of time. And thanks to you guys for attending this presentation, Novedge's Best of the Best webinar series. Just want to give a little background on us here at Novedge in case you're unfamiliar. We're the leading online design software superstore. Not only do we have the best prices around, but our staff is extremely awesome. Call, chat with us at any time if you have any questions about pricing or anything. We'd love to hear from you guys. The last thing I'd like to bring your attention to before we sign off is there is an example. We have Scan&Solve for Rhino and the prices there. But yeah, the last thing I want to mention here real quick is Rhino Jungle. It's an online we've created to help foster the collaboration between Rhino users. We have a ton of stuff, a ton of resources for Scan&Solve. We like to integrate our stuff with the actual Scan&Solve community that Vadim and Michael mentioned earlier. So either shoot over to there or head over to Rhino Jungle to get a ton of resources to help you on your way learning Scan&Solve. If you have any questions, there's a ton of users on there that would love to help you guys out. So again, I don't know, Michael or Vadim, if you guys wanted to add anything really quick before we sign off.
No, thank you. And I guess I just want to point out that if you go to www.scanandsolve.com, you will see all the links, including free download for evaluation copy and lots of all resources. And we will be very happy to reply to any questions or follow up by email or any other way. We would love to hear from you people.
Yeah, I will shoot everyone an email with your guys' emails so that they will be able to contact you. Again, we just ran out of time. Otherwise, we would have got to as many questions as we could. So having said all that, we will see you guys next time.
All right. Thank you.
Okay. Thank you.